So now for something completely different, I'll tell you about some recent developments in HOD modeling. Particularly, I will tell you about our recent work in modeling the distribution of galaxies and matter down to small nonlinear scales. And just to clarify, when I talk about small scales, I'm talking about a few hundred kiloparsec. So if you're interested in modeling galaxy formation, there are different kinds of models you can use. There are hydrosimulations, scientific models, empirical forward models, like, for example, universe machine, subhalo abundance matching, and finally, HOD modeling, halo occupation distribution. And if you arrange them like this, you can say that models on the left are more physical and models on the right are more empirical. And you might wonder why we would use HOD modeling to learn something about galaxies. Well, another way to look at this is to say that models on the left contain more assumptions and models on the right have less. And similarly, models on the left are computationally expensive and models on the right are computationally cheap. So I can run an HOD model and make predictions for various observables like number density of galaxies or galaxy clustering in just, let's say, a millisecond. And so we can fully quantify all the uncertainties in HOD model parameters, and because they contain so little intrinsic assumptions, we can use the results on the galaxy connection to infer our understanding or inform our understanding of galaxy formation. And so there have been some very interesting developments in the field of HOD modeling in recent years. So a traditional way to do HOD modeling is what's called the halo model. In this way, you quantify various statistical properties of the matter density field and of dark matter halos. Like, for example, the number density of dark matter halos, halo bias function, mass concentration, etc. And you combine this with your model for how many galaxies live in a dark matter halo as a function of its halo mass. And you can make predictions for various observables like the galaxy clustering. Now, the problem with the halo model is that it's not very accurate on small scales because you have to rely on certain approximations and also because some of the ingredients in your model, like the halo bias function or number density of dark matter halos, is not super accurate. Additionally, the halo model cannot take into account what's known as galaxy assembly bias. So what is galaxy assembly bias? Traditionally in HOD modeling, it was assumed that halo mass is the only variable that determines how many galaxies live inside a dark matter halo. It means you have two dark matter halos that either formed early or formed late. Doesn't matter if they have the same halo mass, they will always have the same number of galaxies. But this is not really a realistic model. In fact, any kind of realistic model of galaxy formation will tell you there's a correlation between halo formation history and how many galaxies live inside a dark matter halo. And so generally, if there's any kind of correlation between the galaxy number and any halo property besides halo mass, that's what we call galaxy assembly bias. And taking this into account is very important because it affects all observables that we look at, like, for example, galaxy clustering or gravitational lensing. And so therefore, it has been shown if you do not take into account galaxy assembly bias, any conclusions you draw from modeling nonlinear scales could be severely biased. Like, for example, conclusions you draw about the galaxy halo connection or about cosmology. And so the next step in this HOD modeling is then to take a simulation of structure formation, identify dark matter halos, and directly populate those with galaxies, and finally calculate all those observables. In this way, you don't rely on any approximations of the halo model, and you can also trivially take into account galaxy assembly bias. The only problem is that you cannot vary cosmological parameters. You're stuck with whatever cosmological parameters were put into your simulation in the first place. And so as I will show later, you have to wonder whether whatever you find out about the galaxy-halo relation could depend on cosmological parameters. And so the final step in this HOD modeling business is then to run multiple cosmological simulations that efficiently sample your cosmological parameter space. And now you also gain the possibility to vary cosmological parameters and see how it affects your conclusions. There's only one final problem. If you want to estimate parameter uncertainties, we typically run an MCMC chain. This would require you to run thousands of likelihood evaluations. And naively, this would require you to run thousands of simulations, which is computationally just infeasible. And so in recent years, several groups have developed clever statistical methods that allow you to explore cosmological parameter space while only running of, let's say, 50 or 100 cosmological simulations. And so one such approach is known as emulation, and we've also developed our own approach that we call cosmological evidence modeling. And so this has only been possible in recent years, but as I'll show you, there are many interesting applications at the intersection of both galaxy formation and cosmology. So one such application is the well-known discrepancy that arises when you model large galaxy surveys down to small scales. So for example, here are results on the recent on the Barron Oscillation Spectroscopic Survey. So the BOSS survey is a spectroscopic galaxy survey of luminous red galaxies at moderately low redshifts. We first assume the best fit Planck CMB cosmological parameters and no galaxy assembly bias. And then we fit an HOD model to the clustering of galaxies. That's what you can see here. This is the predicted correlation function as a function of pair separation RP. And then we show that this HOD model fitted to the clustering does not correctly predict the small-scale lensing signal. So that's what's shown here. This is the ratio of the observed to the predicted lensing amplitude. And here, lensing amplitude is measured in the so-called excess surface density delta sigma. So we see that if we fix cosmological parameters and we assume no galaxy assembly bias, then the fit to the cluster of galaxies tightly constrains this lensing amplitude to within around 5%. But we also see that it falls short of that the actual measured signal falls short of that by up to around 30%. And this discrepancy is particularly strong on nonlinear scales. So basically, I found that there's too little matter around BOSS galaxies than would have expected based upon their clustering signal. And so this is a well-known discrepancy that we have shown here for the BOSS galaxy survey, and it's also previously been found for SDSS. So again, if you assume Planck cosmological parameters and no galaxy assembly bias, basically galaxy clustering and galaxy-galaxy lensing are incompatible. And so this is one of those interesting applications of this new generation of HOD modeling. So for example, in our paper, we address whether galaxy assembly bias could potentially explain this discrepancy here. That's what you can see here. So we now fit a model, an HOD model, to the cluster of galaxies, but we now allow for galaxy assembly bias. So again, in other words, we just allow for the formation history of a dark matter halo to inform its galaxy content. If we allow that, then immediately the possible range of lensing amplitudes gets larger by around a factor of 3. You can see here by comparing the model with assembly bias to the one without. And so generally, galaxy clustering alone places not very strong constraints on galaxy assembly bias, so we cannot tell from clustering alone whether galaxies tend to live in dark matter halos that formed late or early. But if you combine it with the lensing signal, we would say that the lensing discrepancy can be reduced if galaxies preferentially live in dark matter halos that assemble late. At the same time, we also see that galaxy assembly bias alone cannot really explain the entire magnitude of this discrepancy. So we also have to look at cosmological parameters and how they affect this. So now we fit an HOD model to both the cluster and lensing at the same time. We can then marginalize over HOD parameter uncertainties and get cosmological constraints. And we get particularly strong constraints on the parameter combination omega matter and sigma 8. And so you can see our constraints here in blue compared with the Planck CMB results in green. And so you can see in order to really resolve this discrepancy purely by a change of cosmological parameters, you would need cosmological parameters that are substantially different from the Planck CMB findings. And so in our paper, we argue that we probably need a moderate change in cosmological parameters coupled with galaxy assembly bias and possibly also some strong AGN feedback that ejects some of the gas around massive LRGs. But this kind of result is very interesting in the context of other studies that make very similar claims. So for example, here's a study from SDSS, small-scale clustering by lensing, Marcello Cacciato. Their results are shown here in blue compared to Planck in yellow. So they're also very similar. And there are other studies, for example, based on clusters or based on the hypersuprime-Kim cosmic shear that make very similar claims. So all this adds to some growing body of evidence that there is tension between the low redshift universe and observations of the Planck CMB. Another really exciting application of this new approach of HOD modeling is the Redshift-Space Clustering of galaxies. So here we make some forecasts for whether we can use the Redshift-Space clustering of BOSS galaxies to tell us something about the galaxy assembly bias of them. So this is only based on mock data, it's not real data. But we parameterize galaxy assembly bias by this parameter that we call ASEN. If ASEN is 1, that means that galaxies tend to live in dark matter halos that assemble early. If it's -1, they prefer to live in dark matter halos that assemble late. And if it's 0, they have no preference, which is just a no assembly bias case. And so this is just some mock data. And so you can see whatever we infer about ASEN depends sensitively on the cosmology that we assume. And so this here, the growth rate F sigma 8. So if we assume, let's say, 0.4, we would infer ASEN to be +1. If it's 0.55, would infer ASEN to be almost surely -1. And so you can see that whatever we infer about galaxy assembly bias, again, depends sensitively on what we assume about cosmological parameters. And this entire range of cosmological parameters is still somewhat viable within the Planck results. At the same time, we also show that with this new generation of HOD modeling, we can actually marginalize over or simultaneously constrain both galaxy assembly bias and cosmological parameters, and for example, get cosmological parameters on F sigma 8 that are to within ±2%. So that's some of the strongest constraints on this cosmological parameter, and much stronger than you would get from, for example, analyzing larger linear scales, as it's commonly done in cosmological studies. And so these are my takeaway points. Small nonlinear scales are a very interesting probe of both galaxy assembly bias and cosmology. And now we finally have the tools that we are able to constrain both of them at the same time. And so, for example, when we analyze the small-scale clustering plus lensing signal of Blas galaxies, we argue that there's evidence for some tension with the Planck CMB results, and at the same time, there's probably also some level of galaxy assembly bias. And similarly, if you want to constrain galaxy assembly bias from Redshift-Space Clustering in Blas, we see that there is some degeneracy with cosmological parameters. Thank you. Right. So you're talking about this thing here, this discrepancy? Yes. So these predictions here are based on dark matter only simulations, so they don't include the impact of AJN feedback. If you include AJN feedback, you can get a small effect, but it's never not that large. So it's typically around, I'd say at most 10%. So this is probably contributing to that discrepancy, but it's not, it can't explain this by itself.
Always seems to be kind of an oddball out. Is there any room left for systematic uncertainties in the way people measure this stuff that could just resolve a lot of this? It's a little alarming with always weak lensing that drives a lot of this stuff. It's so hard.
Certainly. So this is based on CFH-GLS. So it's one survey. Surely we would want to look at other surveys as well. For example, with HSC, certainly there is some room, and there is some tentative evidence that there might be some bias in the lensing signal. We definitely need to look into this as well.